Recording in progress.
All right, are we all good? Yep. All right, awesome. So I shared a couple links in the chat already. So I have some slides that you can follow along with, and then I also have some code on Colab if you want to play with it. So I took just a few of the concepts and I turned them into code, and then I just made it a little bit easier if you want to just kind of mess with some numbers and actually play with things and just see how they interact. You can play with that. I'll walk through it as we go through this slide. So you don't have to run it on your own, but if you want to, it might help you build a little bit more intuition about some of these things. Um, so for this chapter, we were looking at analytic geometry. A little bit building off of last week, but not that much. Like Ted said, it's a little bit independent. So um, the first part of the chapter, we were looking at norms, and so we can think of this as the size or the magnitude of a vector. So they gave us two examples. They gave us the L1 norm and the L2 norm. And so that the L1 is called the Manhattan norm, and I kind of think of this sometimes as like when you're in a block in Manhattan, you can't go straight through the buildings. You have to go kind of around the corners. And so what this graphic is showing, this is the L1 norm over here, and this is showing all of the points that are one unit away from the origin, essentially. So this square here, all of these, this whole square is 1 unit away from the origin. And then we also have the Euclidean or L2 norm, which is this over here, which is showing this circle. And so this is sort of a straight line to the space. So in contrast to the Manhattan norm. Um, so just looking at the properties of norms, I'll show this in code because I think that means a little bit more to me than just all of the equations. So you have they're absolutely homogeneous. And so what this means is if you multiply by some number lambda, it scales it up a certain amount, and that will be the same scaling as inside the norm as outside the norm. And we can look at that in the code in a second. And then there's also the triangle inequality. And so this is basically saying that the distance of the vector x plus the vector y is going to be less than or equal to the norm of x plus the norm of y. And I'll show this in code in a second, and maybe that is a helpful different view for some people. And then it's also positive definite. So it's greater than or equal to 0, assuming that it's not actually 0. So the norm of 0 should actually be 0. And then I'll flip over to this code for a second. And so what I've done in this little Colab notebook is I've just got some functions to show some of the stuff that I'm talking about here. So I've got NumPy and Matplotlib, so I can plot some stuff and also just define the norms. So here's my definition of the L1 norm. And I tried to do some of this stuff more manually because in a lot of these things, like NumPy will just already have these built in. But I tried to say, okay, here's the nuts and bolts rather than just saying call this function. So like I've defined the L1 norm as the absolute value, and then the sum of whatever my array is. And then the L2 norm is the matrix multiply of the array and its transpose, and then the square root of it. So I have these two functions, and I can use that throughout the rest of the notebook. And so I have this random vector that I've created, so -2, -5. And then I can measure the L1 norm of that. And I get 7, and this is kind of simple. It's just saying -2 plus -5, basically, the absolute values of those. And then I can measure the L2 norm, and that will do the same thing, but with the L2 norm, and that's just following along with this equation. And then what this is showing is the property that they're absolutely homogeneous. So what this is saying is basically if you multiply by 3 on the outside, it's the same as multiplying 3 on the inside. So if you multiply 3 to each of these values, it's scaling it up in a linear way. And so it's going to be exactly the same on the inside and the outside of the norm. Um, and then looking at the triangle inequality piece of this, um, it's breaking it down into various different pieces. So we can say, look at the L1 norm of the vector x individually and L1 norm of y individually and add them together. And that gives you 14. But then if I look at the L1 norm of x and y together, I add them. And so these actually cancel out. So then add these together, this becomes 0, 0. The L1 norm of 0 is 0. And so it turns out that the length of both of them added together is greater than the length of the vectors added together and then measuring the norm. And so if you plot this, you can see what that means. So if we look at -2, -5, you're going a certain direction, and then with the 2, 5, you're going all the way back to 0. And so if you're measuring the norm of that, you're back at 0, 0. So there's no distance. But measuring it separately, you're saying, okay, it's 7 this way, 7 that way. And so that's why it's a greater distance in that way.
Hey Ryan, sorry to interrupt. When you
Yeah.
go back to the collab next, would you mind making the font a little bigger?
Yeah, yeah, I can do that. Yeah.
Thanks.
Let me do that right now. Is that better?
Thank you.
Yeah, yeah. Um, so one of the very important parts of this chapter was teaching about inner products, and so this kind of measures the alignment or the angle between two vectors. And so we looked at dot product previously, and this is kind of a generalization of that. You can have various different kinds of inner products. So a lot of the time we'll be using the dot product, but there's different options that can be done there. And so one of the things here they showed you can format it in different ways, the dot product. So x transpose or transpose of x times y is the dot product, or you can also do it in this format. And so I showed that also in the code here. So the simple version saying transpose of x, matrix multiplied by y. I think I need to redefine that. Hang on. Yeah. So we get this value -29. So that's the dot product between the two of them. Or we can just directly use the numpy function saying, here's the dot product. And then this is the other formulation that they had, basically saying multiply xi times yi and sum them all together. And then you see that these are all the same thing. So these are just the different formulations of the dot product. And then here's some, here's one of the examples. So they're teaching the property of symmetric positive definite matrices. And so they gave us these two matrices that we can look at. We have A1 and A2, and they're symmetric because if you take the transpose of them, they're still the same thing. But then we're also judging them for whether they're positive definite. And so we can look at A1 and we can see that it is. So multiplying all of this out together, we see it yields this equation. And so what this is saying is that it's guaranteed to always be positive essentially. And if you look at this, you can understand why this is the case because both of these terms are actually squared. So there's no possibility for them to be less than 0. So this is squared, this is squared. So both of them have to be positive. There's no way for them to cross over into the negatives. So that's for A1, but if you look at A2, and they multiply it all out and they get this equation. And then you see that because it's actually negative x squared, this can actually be negative at certain portions of this. So this is one example of just symmetric positive definite matrices. So A1 is symmetric positive definite and A2 is only symmetric. So then we were looking at lengths and distances. And so, yeah.
Mind if I jump in for a second?
Yeah, go for
So one comment I have is that I've struggled for a long time with the idea of inner products, trying to find some intuition for what is an inner product. And if anybody has a good one, please share it. But basically, what I've settled on is I just sort of have this algebraic notion of an inner product, which is if it fits this pattern, if you can use it this way, that's the formal definition of an inner product. So it is one because we said it is one, but I don't really have uh, sort of a greater, intuition as to why this would and wouldn't be. I mean, like, again, I can do the test and say, oh, you get a negative number. It's not positive semi-definite. It's not an inner product. But like, why? That's the definition, right? So anyway, I just wanted to share in case other people are also struggling that for me, basically what I've settled on is I have to remember the rules and understand that if it follows this pattern, if it if it walks like a duck, if it quacks like a duck, if it whatever, then it is a duck. And inner products have all these wonderful properties based on how we've defined it. But whereas something else, like I might have some intuition that, like, oh, if you're measuring something in the real world, it has to kind of observe the triangle inequality. It's like, so anyway, uh, open to anybody here or on Slack can share if there's wonderful, better intuition out there somewhere.
Well, you can look at the scalar product as projection. So numerically, it is a projection to this particular vector, to one of the vectors, I mean.
Right, but some matrices are valid inner products and some are not, and why? That's what I haven't quite. Yeah, sorry, I don't want to take us too far down the rabbit hole, but I just because for a lot of things for me, it's like, okay, can we have a good, strong intuition? What's going on here? And this is one of the ones that I've yet to find one.
Yeah, yeah. So I'll move on to lengths and distances. So one of the things that I was thinking about is, like, to me, I view the norm as sort of like the distance from the origin. And then we also have lengths and distances, which can be distances to other vectors, other points, other things. And so we have to be able to measure those as well. And so this is like Ted was saying, there's different ways that you can define inner products. And so this example on the left here, they're showing, okay, we could define the inner product as a dot product, but another valid option is also this matrices here. It matches all of the criteria to define an inner product, but it gives us slightly different interactions than just the dot product. And so that's interesting because you're defining distances, you're defining angles, you're defining all of these stuff based on your inner product, and so that kind of changes your whole space. You define whether things are closer or further differently and what their orientation and all of that stuff. So it's interesting to plug in different inner products and see how all of those interactions kind of change. So one of the things that they mentioned in this part of the chapter was that this mapping of vectors to distance can be called a metric. And so this is an area that I've been working in more recently. So we talked, I don't know if it was last week or 2 weeks ago, about the finding the layout of the Coke drinks and then figuring out what the drinks actually are. That kind of modeling is a kind of metric learning. So that's a whole area of study of saying basically take this data and then map it to similar places and measure the distances so that similar data is close and different data is further away. So I just wanted to point out they mentioned the word metric, but they didn't really talk about kind of there's a whole field of study of that. So I mentioned this word, but now talking about it a little bit more formally, we're looking at angles and orthogonality. And so the inner product can help us measure the angle between vectors as well. And so this tells us how similar the orientation of vectors are. So vectors are orthogonal when their inner product is zero. So I think of this more simply in the like 2D case of like you have something that's a 90-degree angle. This is orthogonal is scaling it up to 3D, 4D, everything beyond that. You have something that's perpendicular or orthogonal. Um, and so if the norms are also one, then it's orthonormal. It's not just orthogonal. And so I have something in the code here where what I'm doing is I'm measuring this angle using the dot product. So I have two different vectors here. I have 1, 0 and 4, 0. And if we think about this for a second, what would we expect the angle to be between these? They're going in exactly the same direction. One of them is just a scaled version of the other. So we can see that it ends up being 0 degrees. So they're going exactly the same direction. Their orientation matches. And then we can plot this and we can see, oh, okay, so there's one line that's going from 0 to 1, and then there's another line that's going all the way to 4. It doesn't show well because they're perfectly overlapping. But we can try this, just modifying the numbers for a second. So plug in 1 instead, and then we can say, plot all of these again, and we can see what these are. So we can see one of them is going from 1, 1 and 4, 1. So we have our 4, 1 and what should be our 1, 1. And then we're measuring the angle between these. And so this is defined with the dot product and the L2 norm between them. And so we can measure it in radians and we can also measure it in degrees. So we can see this is about 31 degrees and that kind of looks about right. We know what 90 degree is. This is probably 3 of those roughly. So this is just showing how we can measure the angle between two vectors. So now looking at orthonormal bases, the next section of the chapter. So orthonormal means that they are all of the basis vectors are orthogonal and they also have a length of 1. And so one of the things that they spent a bit of time on is that using Gaussian elimination on linear independent vectors, you can find an orthonormal basis, and they called that method the Gram-Schmidt method. So you can take something that isn't orthonormal and make it orthonormal. Here's the basis in order to line that up with these properties. And so a very trivial one of these, a very trivial orthonormal basis is 1, 0, 0, 0, 1, 0, 0, 0, 1. So now we have a 3D orthonormal basis set. And then they also showed slightly less trivial versions. So here's a 2D version, and they're saying, here's our first basis, here's our second basis, and then they're showing, hey, this actually meets all of the properties still because the basis vectors are orthogonal to each other, and they still have a length of 1, even though it's this different different than the trivial case. So the next concept that they talked about was the orthogonal complement. So I was looking at this in the book and I wasn't entirely understanding the visualization. So I actually took this to ChatGPT and I said, make a plot of this. And I like these plots a little bit better than what was in the book. So this is showing you have this 2D space and then you have a certain subspace of it. Let's call this W. So we have subspace W, and then we have the complement of it, this red line. And this is showing that every point on this subspace is orthogonal to this other subspace. So we have W, and then we have W complement. And so we can see that for all of those points, they're orthogonal there. And then we can also see this in 3D. So we have a 3D space that has XYZ, and then we have a subspace W that just has this vector and this vector defining it. And then we have another orthogonal complement saying this is essentially the z-axis. Whatever you do along this z-axis is always going to be orthogonal to this other subspace W. And in the next section, what they were talking about was there a comment there?
Yeah, do you mind if I just do a little bit of color before we move on to the next?
Go for it.
So two quick comments. So one is I remember in high school taking geometry, and like we just called it geometry, but officially, like I think the textbook somewhere said Euclidean geometry, right? And so, it's only this many years later that I realized this entire geometry and everything about it is based on choosing that one inner product, and that there's entire geometries you can have where you use a different inner product rather than just what I would call like the standard dot product or whatever. So so if you get into anything with like kernel learning, then like that's the part where like my brain starts to hurt a little bit because you're now no longer using Euclidean geometry for things. And then the other comment quickly tying to last chapter is if you have an n-dimensional vector space and you have a d-dimensional vector space, I think it says it in the book, but basically you will always have n minus d dimensions left over, and there will be basically exactly n minus d dimensions in your orthogonal. So it will never be the case that you have a three-dimensional space and a two-dimensional subspace, and you can't find that remaining one dimension, that for some reason, these are all linear things. And so when you take out d, you always get exactly n minus d left for the orthogonal.
On the figure on the right, we can see a plane, a two-dimensional plane, and perpendicular z-axis. According to what you just said, this z-axis, which is a complement to this plane, is supposed to be one-dimensional. But geometrically thinking, we can create a plane that falls inside this z-dimensional space, but it won't be a complement. I mean, but it could be potentially orthogonal to this plane. Like two planes could be orthogonal to each other, right? Then why it won't be a complement anymore, or what? I'm a little bit confused because the definition is really it's not hard to understand. But when I just see this figure, I just think, okay, what if we just create a plane that goes through the z-axis?
Okay, could you guys hear the question? Because I could summarize it if you couldn't hear it. Oh, you didn't hear? Okay.
I heard parts of it, but if you could.
All right. So very briefly, the figure on the right shows 3 dimensions, a 2-dimensional subspace, and then orthogonal to that, we have the red 1-dimensional space. But the question is, hey, in geometry, we can have a plane that's perpendicular to the blue plane. It doesn't just have to be the line. So why are we saying it's just the line? Is that a reasonable summary? Yeah. So the thing we have to understand is that here we are talking about vector spaces, not physical objects. So when you look at that red line, what we're really talking about is the set of vectors rooted at the origin that end somewhere on that red line. Okay, so they're all in this case just up down vectors. If I turn that into a plane, yeah, any vertical line within that plane is perpendicular to the blue plane in the geometric sense, but it doesn't start at the origin. And when we talk about vector spaces, we're talking about vectors that are rooted at the origin. So then you're going to have a diagonal line in that plane where geometrically, intuitively, we say the plane is perpendicular to the blue plane, but those vectors that are not on the red line, that are elsewhere, are going to be not orthogonal to the blue. So it's really the idea that in vector spaces, we're only talking about vectors rooted at the origin. And so then that's how you compare your intuitive idea of perpendicular to the vector space notion, because right, if I were comparing two planes, I would find the point of closest intersection and I would say that's 90 degrees. But we don't ever use the point of closest intersection. We always use the origin for comparison.
If I can just jump in real quick. Hi, my name is Marcel. So yeah, I've been reading papers about these concepts for grad school, and in case anyone is wondering, how do all these concepts tie into machine learning? Well, I mean, first of all, the inner product is in a lot of like basic algorithms, like a support vector machine, principal component analysis, regression, and orthogonality can be used for feature selection and regularization. And orthonormal basis, I just read a paper about this yesterday, can be used for function approximation in reinforcement learning. So yeah, just in case anyone is wondering, why do we need to know this stuff?
Very cool. Yeah, so maybe half of those things we're going to see. So the way this book is organized, it does 7 chapters is the basic math and then does the applications. So we'll get a few of those. We'll get PCA, we'll get SVMs in the second half of the book. I'll also just throw out there, I recently just read a paper called Representation Fine-Tuning, REFT. So there's LoRa, if you guys are familiar with. And then what REF does is rather than modify the weights, it directly modifies the activations coming out of the like transformer layers and stuff like that. And inside of it, one of the things they do is they say they want a matrix. It's that has orthonormal. Actually, I think it's just orthogonal, but it has orthogonal column vectors, and they say it works really well. But I think they have to do that Graham-Schmidt thing that Ryan just showed a slide or two ago. Theoretically, after every weight update, after every step in gradient descent, which is expensive. Okay. So they come up with an alternative that does not require orthogonal columns, and it works almost as well under most circumstances. But just saw, in fact, there where they were specifically taking advantage of this orthogonal property, and yeah, we'll see. I forget if it's later in this chapter, next chapter, but there's other properties that orthogonal matrices have. All right, thanks, Ryan. So, thanks for allowing the side comments.
Yeah, thank you. So in the next section, talking about inner product of functions. So this is kind of going beyond just fixed size vectors. So imagine we have our like vector of length 3, and we can scale that up and say do it for an entire function. So you can think of this as like an infinitely long vector. You plug in a bunch of values into it and you get a bunch of values out, and you can kind of do an inner product of the whole function and all possible inputs, outputs. And so here's one of the examples that they had in the book. They're showing, okay, here's one function sine of x and another function cosine of x, and then you can calculate the inner product of it by doing the integral over this whole equation that they defined. And then you can see what the inner product of it is. And so they put some limits on it. They said negative pi to pi, and then they get a value in the end of 0. And so that's showing that sine and cosine are orthogonal functions. So you can have orthogonal vectors, but you can also have orthogonal functions. So I think of this as like infinitely long vector. So when I was originally looking at it, I was like, how do you possibly do inner product of a function that this kind of shows the way you think about it, where it's like you can plug in 1,000 values of it or infinitely many values to it, and that's kind of showing how you do it for a whole function, and you do the integral over that. So the next section, they were talking about orthogonal projections, and this is a very, very important piece. It's kind of core to a lot of the different things that we do with machine learning. So PCA, neural networks, linear regression, they can all be a different view of this sort of dimensionality reduction. So for some, like the neural network, you might have nonlinearity that kind of complicates things, but for PCA and linear regression, this is a good way of looking at it. And so you can think of this as finding the shortest path to a subspace. And so that shortest path actually depends on the inner product that you choose. So for the dot product, it might be one thing, and for the other one that we saw, or any of the different options that you can pick that might change what you choose as the shortest path. And so we can see in these graphics here, we have a certain space, and then we can see that we're projecting down onto the spaces vector B, and we're saying this is the shortest path defined by our inner product over here. And then with this, now we've kind of shifted it here, and we can understand based on the sine and the cosine of this, we can figure out the angles and the distances and all of the nice things that you can typically do with triangles. So this is the sort of 2D to 1D view of this, and then here's another one in 3D, and you can see that we're projecting down to this plane here, and we're saying this is the shortest path onto the plane view. And so this is a very core concept. And one of the interesting things about this too is there exists a projection matrix that you can find, and that will project all of your points from one space into the new subspace. And so once you find that matrix, then you can just basically say map every point in this space to the new space just by applying that projection matrix. And that's useful in various different ways too.
So sorry, Ryan, if I
yeah.
color one more time. The thing that I learned reading this chapter is I knew what projections were, and like I said, from high school geometry, I had a pretty good intuition. But I did not know that projections were a linear transformation. I didn't know that a matrix multiply could actually do projection. I knew I could do one, like if you just say like, oh, here's an object and the sun at noon casts a shadow, and that's like a project. Yeah. So yeah, that was a big one for me. So then it's like, oh, okay, well then now if it's a linear transformation, that means it can be performed by a matrix multiply. And then you get these really weird things that it says in the book that like a squared equals a. And I was like, really? How many matrices are there where like the square of it is identical to itself? That can't be that many. And then it's like, oh, wow, it's actually like, I mean, any projector, it's like, it's actually reasonably easy to construct a matrix that it's square and therefore cube and whatever, all powers are identical to itself. but it's not the identity matrix. So I was like, oh, wow, I had no idea until I read this chapter.
Yeah, yeah, thank you, Ted. Yeah, so moving on, so this is the last section of the chapter, is talking about rotation. So rotations, at least to me, are kind of intuitive. We have rotations in our daily life, but the actual properties of it preserves the angles and the distances. Um, so if you have some space and you say, I'm going to rotate it on this axis, all of the things stay the same distance to each other. They all have the same angle between each other. All of that is preserved. And so they showed the various different 3D rotations. And so they're showing that you can rotate on each of the different axes. And so here's the formula for rotating on the first axis, the second axis, and the third axis. And so this is useful in a lot of stuff. So if you're trying to rotate an image or rotate pretty much anything, you can use these sort of formulas depending on the dimensionality of your space. So I have one time where I had to actually directly do this. I had this. I'm trying to trace the sheets of the papyrus from the scroll work that I did. Some of you know about that, but essentially trying to trace along the sheets of the papyrus. And every time I was moving it along, I wanted to reorient it to keep it so that north was up, and I was staying in the same direction even when I was spiraling around the papyrus. So I wanted to copy paste that code over here, but it was too complicated to kind of surgery out of it. But it's just kind of interesting because I actually directly had this in some code at some point because I needed to align things in order to keep it in the correct orientation when I was passing it to my model that was learning this rotation. So here's rotating by 112.5 degrees, and here's another rotation of a robot arm learning how to actually rotate the blocks. So rotation's very common concept in machine learning, just image manipulation and computer graphics and everything like that. So this is the last section. I wanted to call out next month we'll be doing matrix decompositions. So that'll be January 18th, next chapter of the book. I haven't read that far. Maybe some of you have, but yeah, that'll be January 18th. So next month after the new year.
Awesome. Thanks, Ryan. So I think we have time for some questions, discussion, look at the exercises. I don't know if you have anything formal planned, but we can kind of go from here. So again, probably easiest if you're on Zoom to raise your hand, and in the room, if you don't mind, I don't want to be like school teacher Ted, but like it'll be easier to cue people if you raise your hand. So we have a hand raised in the room. So
Basically, we can rotate and then split the object, and then it will be nonlinear information. Like how we can really define if this matrix by which we multiply our data will be linear or non-linear transformation rotation.
so what was the second thing? You said rotation and then what?
Second thing is that basically we can multiply our data by some like matrix. For example, if that example that we saw with cosinus functions, if for example we have different angles, then it won't be the linear transformation. It would be the non-linear, like we would squeeze or
Okay.
like more sparse on our object data. Yeah, I'm wondering maybe even if we keep this angles equal, but maybe equally good instead of like, because for a cosinus sinus minus sinus to cosinus, what if it would be plus sinus to cosinus, it would be a linear transformation. So I mean, how to define if that just linear rotate the objects by preserving all the angles in that, for example, where like if, how we really can define between linear and non-linear in this things.
Yeah, so let me try and summarize that at I may not capture all of it, but sort of like what makes a rotation, what are the things that have it be a linear transformation versus not a linear transformation is sort of the gist of the question. So Ryan, I don't know if you want to take a stab at it or I can take a stab at that one.
I'll let you go for it. I don't know if I heard the whole thing.
All right, Liam, if you want to take a stab at it, yeah.
I was going to say, like, how I understand it, the rotation matrix has to be an orthogonal matrix. So by definition, because it's orthogonal, and I haven't like tried to prove this, but because it's an orthogonal matrix, it must be a linear transformation.
Yeah.
Right.
Yeah. So in case you guys online couldn't hear, so what we talked about is a rotation has to be an orthogonal matrix, and orthogonal matrices are obviously linear transformations. And again, similar to the point before, you have to remember we're only talking about vector spaces here. So if you start talking to somebody in robotics or photography or whatever computer animation, okay, they're not centering everything on the origin. And so they have some slightly different operations that are valid for them that we don't talk about in vector spaces, because we're not talking about a physical point. We're talking about a vector as the concept of the direction from the origin, okay? There's other things you can do with physical points. You can translate them. That's no longer a vector space. You cannot translate things. You can stretch things and you can rotate things. So another way of thinking about it is that ultimately rotations are just changes of bases. So all you're really doing when you rotate something is you're saying, I'm using this orthonormal basis that's pointing in different directions instead of the standard basis 1, 0, 0, 0, 1, 0, 0, 0, 1.
And don't you need like 2, 3 dimensions to do a rotation? Or is that what you were talking about the identity before of like 2 minus n dimensions? You need like 2 dimensions to rotate around in dimensional space?
The question is around how many dimensions you need, and I'm not quite sure how to answer that. But basically, if your vector space is n-dimensional, then there's basically n minus 1 degrees of freedom. So in 2D, you can just rotate in one plane. In 3D, you sort of have 2 different I don't know if degrees of freedom is the right way of saying it or whatever. In the book, they represent it as you can compose 3 different rotations around the 3 standard basis axes, okay? But that's not uniquely determining a rotation. There's more than one way you can get to the same place if you combine 3 rotations. If you boiled it down to 2, that would uniquely determine a rotation. So I'm not the expert on like the different ways you can express it, but I hope that answered the question. All right.
Yeah, actually, I do actually have a question. If nobody else, I realize I've already talked a lot, but actually, in the chat, she mentioned affine subspaces, and it's kind of like in a more general sense. I'm wondering, like, part of the chapter was projecting onto, say, like an affine subspace as opposed to just like a vector space. Projecting onto just like a vector space is kind of intuitive, and it's kind of like, linear regression sort of does that. But like in a machine learning context, when would like projecting on an affine subspace sort of intuitively be more like what's going on as opposed to just on like a vector space or something?
Yeah. So the question is, when does like sort of the projection onto an affine space matter more than the projection onto a vector space? So I believe the best example I can think of is if you think about Dolly and Stable Diffusion and all of these text to image generators. Okay. Um, they have this idea where you take the text and you embed it. And so we talk about embedding it into a linear space. We talk about embedding it into a vector space. But the reality is it isn't. It's probably an affine space, which means that vectors are not rooted at the origin. Okay. And if you've played with one of these models, there's a variable you can set. Now I'm blanking on the name of it, but it's the strength to which you want it to adhere to your text prompt. Somebody can put in the chat because I'm blanking on the term. But anyway, this guidance scale thing that you can turn up or down. The downside is when you turn it up, you may get less diversity, because if it's being very strictly faithful to your prompt, then it doesn't really have freedom to decide how it's going to do things. Okay. And if you turn it down, then you can get a little bit more variety and a little bit more. It's like, oh, I didn't tell you what style. So you did one that was photographic and one that was anime and one that was cartoon, right? But if I'm super strict, then you have to follow. The question is, how do you turn the knob up? How do you crank it? The simple thing you do is you have a text prompt. I embed it into this 128 dimensional vector. I'll just double the vector. I'll double all the numbers. And if I want to make it stronger, I'll triple all the numbers. That does not work if you try and build your own stable diffusion, because it's an affine space. And so if all the vectors are sort of rooted over at this point, x naught, and your numbers all come from the origin, then basically what you're really talking about is this is the direction, which I would call like mostly west to your point. But when you double the numbers, you're moving further north. And so you're actually moving in the wrong direction. So what you need to do is, like they talk about at the very end of the chapter, is you sort of subtract x naught in order to get to something that's centered on 0. And then you see, oh, it's west. Now let me double that. Now let me add x naught back in. All right. But what is that x naught? How do we find that point? That's where classifier-free guidance basically says, and I don't know the exact math, I'm going to butcher this, but basically we trained it with some different classes and we sort of found the center point. And so by finding that center point, that's our x naught. That's what we subtract before we are going to double or triple this. And so that's why you'll see that in early diffusion text to image models, they did not have the ability for you to turn up or down the guidance scale, how strongly it was going to adhere to your prompt. And once classifier-free guidance came out, it's this thing where they train it on it's this weird thing where they train it on classes like dog, person, tree, and then they throw away all the classes. You're like, why would you do that? Why would you train it on classes and then never use any of those classes? It's because they're trying to find that origin point effectively, that x naught point. I've probably gotten the math not super right, but that's the clearest example I could think of where if you thought it was a vector space and you just doubled all the numbers, you'd be like, why is it that that dog suddenly became a cat when I doubled the numbers? Whereas when you use classifier-free guidance, there are distortions that happen when you turn the knob high enough because it's not a perfectly linear representation space. But generally speaking, if you say a cartoon German Shepherd, like you turn it up, you're going to really, really get that. And if you turn it really down, then you may get like slightly different animation styles. You may get a Belgian Shepherd instead of a German Shepherd. You may get other, you know, degrees of freedom because you're not enforcing the direction. Does that make sense?
So I'm just kind of curious as a follow-up, like how did they figure out at some point that like, hey, this might be an affine space as opposed to like that? What do you know? Sorry.
Yeah. So then the follow-up question is, how do they figure out it's an affine space? You can see I'm like a little bit the limit of my ability to explain. My guess is that the first person who figured out the really easy hard way, where they just doubled all the numbers and they're like, darn, my dog turned into a cat. This is not working. Why isn't this working? Oh shoot, it's not a vector space, it's an affine space. How am I going to find that sort of centering point so that I know? And so then basically that's how they were able to sort of say the cat direction is not the direction from the origin, it's the direction from something else.
Oh, just real quick. Hi, it's Marisol again. You're gonna have to bear with me. So this is actually my first time at this meetup, so I'm not quite sure how this works. So at the very beginning of the presentation, I saw that Ryan posted a link to a collab notebook. And that's something I'm interested in, like maybe looking at later. But I don't have access to the Zoom thingy. So is that link gonna be posted anywhere else?
Great question. So we have a GitHub repo.
Oh, okay.
And
It's on there.
And it is linked at the bottom of the meetup description, the book club repo. And so basically, I'm going to post a link to the slides, to the collab, and to the YouTube recording. We don't always do it immediately, but as soon as no, don't say never. That's great because I found some people don't read all the way through the really long description to see the little thing that says here's the repo where you can find things. But yes, if you want any of the things that we're presenting, or if you like miss a week and you want to see stuff. And then just as a side note, all the books that we've done for like the last 4 years, all of those slides and recordings and everything are also in that same repo. So gave me an opportunity to plug it. Thank you. I'll pay you your $5 later. Okay, looks like Ryan's back. Any other questions? Exercises? Anything that people got stuck on with the exercises? Question about, are there any of the exercises to maybe focus on? Anybody else have a vote? I'm trying to remember. I think for me, the biggest thing I'll say was like, I don't think you need to like memorize all the procedures and the whatever. But especially if you're gonna read about like kernel methods, just really getting it in your bones that the Euclidean dot product is only one way in which you can define a perfectly valid inner product, and that other inner products can look very, very different. So I think that was one thing that was a little hard for me. And then I haven't really explored, but the whole idea that if you want to extend this now to functions, right? You can say a vector of length 10 is f of 1, f of 2, f of 3, f of 4, 5, 6, 7, 8, 9, and 10. And if you wanted to know what f of x is for all integers, you could have a countably infinite long vector. And if you want to know what f of x is for all reals, then you need this uncountably infinitely long vector. But that basically you're just recording what is f of every single thing, and there's no good way to enumerate it at that point because reals can't be enumerated. But nevertheless, if you just sort of, again, like think about this algebraically, just go with the abstraction that somehow there's the right order to list all of the things, then this infinitely long vector contains the value function. Then you can get into infinite dimensional vector spaces and sort of, again, for me, I just have to very slowly work through them algebraically. Like if this was only 3D, this is how I would write it. And I'm going to write it the same way, even though it's infinite dimensional. And I'm just going to like not obsess over the fact that it's infinite and I don't necessarily, you know. So for me, I think those were two of the big things. And the rest I feel like is not necessary to do machine learning, but it's always nice to have some intuition around what's going on. And so then some things like orthogonal projections, they always sum up to the total number of dimensions. And like that, I didn't know that projection was a linear transformation. Yeah, I don't think like you absolutely need, but it's just a little bit easier to maybe have an intuition over what's going on. And I actually like Liam's question about affine spaces because we don't in machine learning talk enough about affine spaces. Everybody just says the word linear and they often throw it around as if they're talking about vector spaces. And generally speaking, every neural network type has a bias, and in almost all models, the bias is turned on. There's a few places where you'll see bias equals false, but it's almost always turned on. So we're almost always working with affine transformations, not linear transformations. And it breaks stuff if you interpret it wrong. So again, like, you know, you can use a ResNet. You don't need to know any of this, but it helps to sort of have a deeper intuition around what's going on.
All matter starts from origin, and then we are planning markets, which is the linear document, to find weight matters to do a nonlinear transformation. So it's again, it still could be in vector space after the nonlinear transformation. It just will, like the object will be sorted non-linearly, right? Or
yeah, so asking about neural networks, and then kind of we get to these activation functions. So basically, if you use original ReLU, because the two halves of it are linear, okay, then what you will wind up with is something that is piecewise linear. Okay, so at whatever the ReLU cutoff point is, then everything to the right of it will be linear, everything to the left of it linear, but they will be separate linear functions. Okay, and so when we were doing the last, well, it wasn't the last book, the Understanding Deep Learning book, that was one of the first things they talk about is that when you use straight up ReLUs, you're just dividing things into piecewise linear sections, literally piecewise linear sections, or affine, perhaps is probably the better terms, okay? But they're all linear functions in terms of, you know, for input x between 7 and 9, you're going to get a line with a slope of whatever. And between 9 and 12, you're going to get a line with a slope of whatever. And blah, 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 blah. It's going to be piecewise linear. The reality is now that we use these more complicated activation functions and they're actually curvy, this breaks it, but I think most people, the conventional wisdom, they still think of it as if it were approximately piecewise linear. So you say, I have this Gelu function, so maybe now I'll break it up into like 6, 7 pieces, and each of them is approximately linear, and that's good enough for having an intuition around what's happening in the neural network. sigmoid is hard to talk about being piecewise linear, but the reality is nobody uses sigmoid except as a output transformation for binary classification. So it's never used as an activation function inside. And I think it's not because it's not piecewise linear, but it's because the the slopes that are far from zero are only in a very constrained range. So I think, sorry, I'm like going on and on in here, but like, so I think one of the things people are finding as we're building bigger and bigger and deeper neural networks is that the normalization is really important in order to keep all the values in ranges that the activation functions can do interesting things. If everything's too far left, nothing happens. There's all this negative stuff and the slope's almost zero. If everything's all the way to the right, you're not killing the data, but there's also nothing interesting happening. For learning to happen, you have to have values that are kind of close to zero. Okay. And so, oh, I lost my train of thought a little bit here. But anyway, so sigmoid, because it has such a narrow range in which there is a non-zero gradient, because as soon as you get to like whatever, +2 and -2, everything is just close to zero gradient. Then you pass that through 4 layers that have this happening, and your gradient basically vanishes. You get a floating point underflow. There is no gradient. There is no learning. It's a completely dead neuron at that point. It will never change value. That makes sense?
The exercise is the only one to me that seems difficult with 3.7, because I think that requires you remember the previous chapter.
Okay.
So, like I can't remember now the endomorphism. I have to go back to the previous chapter and the kernel and the image. How do you get the kernel and the image? So I think that's in the previous chapter. You need to go back and.
Yeah, that's a good point. So exercise 3.7, you do have to know the concepts from the previous chapter because it references image and kernel, and it throws out endomorphism, which, you know, I look it up every time I see that word. I mean, there's a few words that I like. Bijection, I've gotten to the point where I kind of actually remember that without having to look it up, but endomorphism, I just look it up. I still, right now, I cannot tell you the definition. If you held a gun to my head, I would make a guess, and I would hope that it's better than a coin flip, but yeah, not sure.
I think it's in the same subspace. It's B2B, and it's linked. I think that's it. Automorphism is bijection. Actually, one cool thing that I wanted to mention about the kernel or the null space is that I thought was fascinating that was covered in the book was that an orthogonal complement to any particular vector is actually the null space. What was it? It was like, had it written down. Yes, the null space is the orthogonal complement of the row space, which is like,
Yeah, that's good. Yeah, so if you have a system of linear equations and you have a solution space, that's in the column space or whatever, then the kernel, the null space, is going to be the orthogonal complement to that. And that's just sort of, again, using this math that if you say had a 5-dimensional space and you have a 3-dimensional solution, then there's 2 dimensions left, and they, how do we say it? When you use that matrix that defines your linear system, you have to get 0. And so basically what you're doing is you're dotting those vectors with the columns of your matrix. And you have to get 0 for every one of those dots, which means that they have to be orthogonal to every one of those. I think this is only true for like Euclidean, but basically, so what we're saying is that you dot anything in the kernel, any vector in the in this null space. If you dot it with your matrix, you're going to get 0. Therefore, they're all orthogonal to everything in your matrix. Therefore, it's the orthogonal projection. And then they have the two same properties where they always sum up to your total number of dimensions n because it's the same phenomenon. That's a good one. Yeah.
Is there any place where you put the answers to the exercises?
No, I just checked the repo. They're all there.
Yeah. So Ryan and I and Liam, we have not done answers to all the exercises, but we did find that there's a GitHub repo where somebody posted their unofficial answers. And I've looked at the answers and I haven't found one that was wrong yet. I found one where it's like, you solved this using a technique that wasn't in the chapter. But so in our repo where it lists all the chapters, whatever, at the bottom there's a link to that answers repo. So yeah, so that's what I did. I sort of checked my answers against that repo. That reminds me though, there was some discussion on Slack about people possibly doing study groups and or working on the exercises together. So I think it's a great idea. If you're not on Slack, I encourage you to join our Slack, and we have an ML Book Club channel. And so you can organize whether you want to meet in real life or whether you want to meet online and work on stuff. But I think that'd be great. It would definitely support both your understanding and also having sort of like an accountability buddy, so that if you're maybe getting a little busy and not sure if you're going to read chapter 4, then you've got someone who you promised to help work on the exercises with, and your accountability buddy can help support you in maintaining your education goal to actually keep going. All right, we are pretty much out of time. Last call. Any last questions about the chapter or the exercises? All right, I think we'll pause here.